we're gonna go ahead and get started. My name is Aaron Magnet. It might show as James on your interface there on the GoToWebinar. It's just the account that we use for this, but I'm a technical marketing manager over here at Autodesk, and I'm going to be showing you how to improve your product performance using Fusion 360 today. So real quick about me, you guys aren't here to hear about me. I'm a mechanical engineer. I went to the University of Nevada, Reno. I'm on LinkedIn, I'm on Twitter. If you want to fire me questions, if you want to contact me, I'm more than happy to help. The goal of today's webinar is to do basically what it says here. And this is better put than I can actually speak to, and I'm not going to read that, but essentially I just want to show you how we can use Fusion 360 to do exactly what the name of this presentation is to improve your product's performance and use this fully integrated system that we have and collaborative system that we have to design some amazing products. So this is, this was actually billed as, I think, two different things. In some places I saw it as advanced FEA, and in other places I saw it billed as, improved product performance. That's the one that I've obviously gone with here. I'm assuming that there is some amount of knowledge in FEA. If you don't have that knowledge yet, I'm hoping that these concepts don't, go over your head. If they do, we're going to be recording this. You'll be able to go on YouTube later and see it. In the meantime, you can go and watch, one of the more introductory FEA lessons. But what we're going to be looking at, we're not actually be doing stress strain. I just kind of used this slide to kind of recap some of the things that we talked about in previous examples, some of the assumptions, some of the setup considerations. I mean, my typical workflow when I'm in the simulation workspace is just to start from the top and work your way down. So in the very first folder, and you'll see me do this, I'm going to be using Fusion 360 throughout this presentation. And I'm going to run through a couple analyses, actually the same one, but a couple different iterations. And hopefully you'll see the process, understand, the steps involved and how to work efficiently and effectively in this tool. So the basics behind the workflow is, to set up your problem, to define boundary conditions, to define loads if you're doing a static stress analysis, to define, thermal considerations if you're doing a thermal study. Once it's set up, you get into discretizing. That's where you break up these complex models that you're all working on into, small elementary pieces, tetrahedrons in our case, and that's when we can go ahead and run the mathematics, solve it. And then, the most important thing, I always like to stress this, is the post-processing. I mean, this is what it's all about. You can actually figure out if your setup is incorrect in your post-processing. It's not going to be perfect the first time you set it up, so use these steps. It's a loop. You get some feedback, you try something else. That works for both the simulation setup, but also for your design, right? Fusion 360 also uses, some adaptive mesh refinement tools which help ensure that your results are spot on. In this case, you can see it's actually helping figure out the stress concentration in the corner of this bracket that you're looking at. So in this webinar, it's going to be kind of a five-parter, mostly in Fusion. I'm going to introduce you to the problem that I'm going to be solving today. I'm going to show you the steps that I went through to set it up and to run it. We're going to duplicate and reuse to try those different designs and shapes and whatever it is that we're trying to accomplish, and we're going to compare those results. We're going to collaborate, and then I'm going to, at the end, as a thank you for attending my webinar, we're going to do a little future release preview. I just got my hands on a future release that's going to be coming out that includes cloud solving, so that's what it is. I kind of just stole my own thunder, but it's pretty amazing. It's just a video, so I'll be able to show you that. So, oh no, I did this slide wrong. That was supposed to show at the very end. Essentially, what we're looking at here is different bulbs, right? So, as everyone probably is aware by now, incandescents are kind of being phased out up to, about a year ago or maybe 2 years ago. Everyone was going to these compact fluorescents because they are, much more efficient. Their lifetime is longer. But now today you're seeing people go to these LED bulbs, and if anyone is on LinkedIn, you might have seen an article I wrote in regards to this. It was just kind of highlighting this for Earth Day. Earth Day was, last Thursday, actually. I think this is a week after, or maybe it was last Friday, I'm not sure. But anyway, there are advantages to LEDs over CFLs. I mean, compact fluorescence, they are much more efficient. Well, sorry, they're not much more efficient than CFLs. I mean, they're way more efficient than incandescents. They're slightly better than CFLs in terms of energy consumption. But where they're better is, some of these other things that you see on here, like there's no slow turn on time. There's no sensitivity to humidity. There's no mercury in there. That's the big one for CFL. So if you've ever disposed of one, there's the whole process you need to go through, and you have to do it properly. I hope everyone does do that. But LEDs have a problem, and that is that the hotter they run, the less their life will be. I mean, if they run at 90 degrees Celsius, they're probably not going to last those 50,000 hours that were advertised, right? And when you're paying $10, $20, $30 a bulb, you want these things to last as long as humanly possible. So if you look at the internals for a LED bulb, it's something like this. Essentially, LED is light emitting diode. It's a diode on a circuit board. There's maybe some thermal interface material, and sorry if that text isn't that legible. And then after that, there's a heat sink to draw the heat away from the diode to keep it as cool as possible. And so that's what I'm going to be looking at in this design and in this consideration here. So what I wanted to try to do was to test multiple iterations of this bulb, right? So the reason for that is, if adding 50 fins to my heatsink has it's a diminishing return, then we don't necessarily want to do that. We want to keep the cost as low as possible. So in using simulation, we can get that cost benefit analysis very quickly and very easily to understand if the changes we're making are going to be effective, and if they're going to be worth the cost, right? So at that point, I'm going to jump over to Fusion, and I'm going to just walk you through every step that I went through to run this problem. So we are looking at a design that I've kind of built up to this point. You just see this is a standard A19 size bulb, and it's got the base and it's got the heatsink. This selection that I have here is the heatsink. After that, you have some sort of substrate material. You have the actual diode, which I made this kind of oversized thing so everyone can see it. And then you have the globe as well. Now, one thing that I've done here in terms of the way that I designed this to make it easier for me to simulate multiple iterations and to build multiple designs of this is I've created components for most of these things that you see in this design. You can see there's the globe component, there's the base component, there's the diode component, etc. And then I called it panel for whatever reason, but that's kind of the circuit board that we're looking at. The one thing that isn't contained within a component are the bodies, the heatsink bodies. And the reason for that will become apparent in a little bit more time as I go to make changes after I've run a simulation, learned a little bit about this. But you can see I have one heatsink that essentially has no fins on it, so it's kind of like a baseline analysis. We can see where we're at with no fins and see how hot it might get. And then we also have a secondary, which has a single fin on it, which we'll be using to build other iterations off of. Now, the reason why I'm not doing that as components is because if I made a change to the original, it's going to change every different configuration. And sometimes I want to test one versus the other and compare those results side by side as much as I humanly can, right? So let's go ahead with that understanding, and let's go and set up the first analysis. And when I go to set up my first analysis, I'm not worried about getting it perfect the very first time. And I hope that none of you here expect to be perfect on your first analysis run. And I hope that it doesn't discourage you if you do get results that might not seem legitimate. So it's just part of the process. That's just how I should conclude that paragraph. So I'm going to jump into my simulation workspace. So just using the drop down under model, I'm going to select simulation. And here you can see I don't have any analyses set up. So this is going to be right from scratch. I wanted to show you as much of the process as possible and show you, what I learned along the way and some of the little tips and tricks that I think might be handy for you. So let's go ahead and select to begin this new study. So just select study from the toolbar. And you can see the 4 different types of studies that we have currently: static stress, modal, thermal, and thermal stress. In this case, we're going to be doing thermal. And you might want to dig into some of the other settings here before we go ahead and start running through this. First of all, I might want to give this a name like baseline or start or whatever you want to call it. This contact tolerance, we'll talk about what that means in a little bit more time. We'll jump into the mesh tab and we'll look and see, I want this to be actually really coarse for this first analysis because it'll enable me to get through more iterations and to show you more of the steps that go along with this. So I'm going to keep that at 10. If this was a final pass, I'd reduce that obviously. That's the main one that I look at here. The other one that I don't want to select here is this create curved mesh elements. And so this create curved mesh elements just changes the order of the elements. It makes them have more nodes, so it takes longer to calculate. Again, that's going to give you better results in the end. But for my purpose, because I'm going to be solving this in front of you, which, can take a little bit of time, so I'm going to have to figure out some things to say while it's actually running. But this will help me not have to think of too many things to say while it's actually running. So we'll keep that deselected. And again, the adaptive mesh refinement, amazing tool, works on assemblies, works on everything. You can turn it on or off. Usually you turn it on for the last pass analysis. It'll help you ensure that your results have converged. If that word doesn't make sense, again, that's covered in another presentation in more detail. Okay, so let's go ahead and let me actually turn that off. Click OK. Okay, so now we're in my thermal analysis here, and you can see that in my browser here, that same kind of setup that you saw in the PowerPoint presentation. So I'm going to just start from the top and work my way down. So the very first folder here in the thermal analysis that I'm going to be working on here is determining what bodies you want to include or exclude from the analysis. And the reason why you might want to exclude bodies from the analysis is if it's not contributing to maybe the cooling of the system, or if it's not contributing to the strength for a stress strain analysis, then you can ignore certain things. And so one thing that I do want to ignore here is the globe. I'm not going to be calculating what's happening above the actual diode. Most of the cooling that occurs in this system is actually convection out of the heatsink itself. So we're going to just turn that off. That's going to save me having to solve for what's going on in the globe, because I don't really care. The other thing is I can expand out my bodies folder here, and even though this heatsink with fin that I showed you a little bit earlier is not showing right now, it's still being included in the analysis. So what I want to do is, again, just deselect it from the list there, and that's going to ensure that it's not going to try to solve or mesh anything that's happening with that heatsink with fin version of this model. Okay, so with that said and done, let's go ahead and just collapse that down. And let's move on to the next step, which is determining study materials. So I don't really assign materials when I'm actually designing currently. Usually I'll come back and actually do it inside of the thermal simulation that I'm setting up here. So I'm going to just right click on my study materials, and let's take a look at what these study materials are by selecting that first item there. And you'll see everything in here, all 5 items, are all aluminum. So, is that accurate? No, that's not accurate at all. The diode's probably not aluminum. The base is probably not aluminum. It's probably some mild steel or something. But the main component that I'm concerned with in this case is actually, the heatsink, which very likely could be an aluminum material. And this is just kind of like a generic aluminum in this case. So let's go ahead and make sure that one's set as original. So I can keep that as that aluminum material. Then we can move on to the next step, which is the driver part, that kind of bed that the circuit board sits on. And maybe this is, a highly conductive material to try to draw the heat away from that diode as much as seemingly possible. I mean, the substrate itself is, insulating the diode to some extent. So I'm going to go ahead and I'm going to change this to maybe like a copper or something. And I'm not pretending to know how these LED bulbs are actually designed. This is really just a nice example to show and demonstrate some things. So if I'm doing something wrong, if you're in this industry and I'm doing something wrong, I apologize, but that's not the point of this exercise. The base, okay, so I mentioned it's probably like some steel stamp, some material. So let's go ahead and I'm going to just hit the T key on my keyboard. I found this to be a nice little shortcut to my mild steels. There's a whole list of steels above this, so this gets me there a little bit quicker. And then the diode itself is actually just going to be, it's going to be a heat source. So I don't necessarily care too much about what material that is. Again, I'm mostly interested in seeing how changing the number of fins on this heatsink are going to affect my results and the temperature in the diode itself. So I'm going to just keep that as aluminum. I don't really care. In the panel here, I'm going to actually assign a material that I created. And it looks like I changed it right before this presentation, this FR4, this circuit board material. Let's go ahead and take a look at some of the properties for this. This FR4 actually is orthotropic material definition, so it's gonna conduct heat differently, through the thickness or along the length. It's gonna do some different things. In this case, I don't really care too much about getting this spot on to what it's actually going to represent in real life. I do just want this to insulate the material a little bit, maybe, or in this case, I actually want it to conduct as much of that heat away from the system as possible. So again, I'm going to just make this copper, and I'm making some vast assumptions here. And again, it's a very simplified approach to a more complex problem. Obviously, there's more that goes on there. So I'm going to go ahead and click OK. And just like that, we've determined some materials for this, whether or not they're, true to real life, that's questionable, but it's just a simulation setup for this example, and to learn about how making design changes is going to affect these results. Okay, so I think I've beat that into the ground well enough at this point. So let's go ahead and determine some loads. And you'll notice that in a thermal simulation, if you've been running static simulations, you'll see there's loads and constraints. In this case, it's really just loads that we're defining. And loads can take different shapes. So I'm going to actually use my marking menu to access my loads. And this is something I've been trying to use a lot more of in the simulation workspace. If I right-click and hold, I can see my thermal load up there in the upper right. The one down here is where constraints would be, but there are none here. So right-click and hold, slide through it. That's going to enable me to define, maybe the heat source for the actual diode. So in this case, I'm going to go ahead and I'm going to change the type from apply temperature to an internal heat. And I'm going to go ahead and I'm going to select the diode. I can either, do it from the graphics area, just left-click and hold, or left-click and select the body itself. What I wanted to make sure of is if you don't actually define it to be an internal heat, it'll start selecting faces, and then you'll have to go and make sure you select the body itself. So the body's selected. A typical diode, I think, will put out something like 5 watts. So I'm going to go ahead and just represent that here. Just type in 5. And you can see there are some different options in here for you, so just pay attention to those. But I think that's all set, so we'll go ahead and click OK to that. Now, if I were to run this right now, there's no way for heat to leave the system, so this thing's going to get really, really, really hot. So let's go ahead and define a way to carry heat away from that diode. So I'm going to go ahead and do my marking menu again, and in this case I'm just going to go straight up. I could go to the right there to get thermal loads, but if I go straight up, it's going to grab my repeat thermal loads option. And in this case, I'm going to change this type to convection. This is just representing, how this heat is being drawn to the surrounding air in this case. And I'll select a couple faces from this heatsink. And you'll notice I'm not selecting all of them. I'm not selecting these top faces. I'm assuming that those are not really contributing greatly to the convection. A, maybe because it's contained within that glow, which might heat up somewhat, or B, it's not it's conducting to the next body. Like, I'm not going to select the faces down here that are actually touching the base part, because that's going to be treated by conduction. That's going to be treated by our contacts that we'll look at next. Okay, so I'll type in a value here, and I'm just going to type it in and click OK. Check out the ambient temperature, 20 degrees Celsius. That looks good. I'm going to go ahead and click OK to that. And it looks like, we're well along our way to setting this problem up. I mean, it really is that easy. Now, if I were to run it right now, again, it's not going to carry the heat away from the diode. And the reason for that is that you need to deal with how bodies can conduct or insulate from one another. And the way that you deal with that in a thermal simulation is using your contacts. So I'm going to right-click on my contacts, and I'm going to create, well, first of all, I did want to look at my degree of freedom view. When I look at this, you'll notice that the two bodies that I've selected to have actually a load at this point show as conducting. So there is some heat source going into or out of those bodies. So that's why those show as green. So that's making the software happy. The ones that are red have not had contact defined between them and some sort of conducting body that you see in here. So let's go ahead and add a manual contact. So it's asking me to do automatic in this case. I'm going to say no, and again, this is just for the lesson's sake. And I'm going to select the two bodies that I want to define to have some contact between them. So we'll start with the diode to the panel piece. And I absolutely love this about Fusion 360. When you select those two bodies, it hides everything else, and it actually makes one of them transparent, the second one that I selected there, enabling me to select the bottom face of that diode to create this contact just so easily. So I'm going to select the bottom face of the diode, the top face of the panel. Once I do that, you can see it's already turned green. It's highlighting that in the degree of freedom plot, which I can keep up while I'm adding different contacts. And just like that, I've created a contact. Now, I don't do that obviously every single time, although I love how easy it is. I'm going to go ahead and I'm going to right click on my contacts, and we'll do some automatic contacts as well. So in just a short amount of time here, it's going to find all the different contacts there. And it is actually pretty significant. Even though that there are only 5 parts, there's a number of different faces that could be potentially in contact here and that are in contact here. And when I was going through this setup, there was actually that contact tolerance, 0.1 millimeters, I think is the default. So if you actually build your models properly, and there's like tolerances built into them, for manufacturing issues or manufacturing tolerances really, it's going to enable you to ignore that small gap that might be there in your design model, and it's going to enable you to find the contact, making it very easy to do things like what we just did there, which was to find the contact between all these faces. So I'm going to expand out my contacts folder, and you'll see that it actually created 15 additional contacts to the manual one that I created there. And this is something that I find interesting. You can actually go and you can delete any manual contacts, but you can't necessarily delete the automatic contacts. So if you want to get rid of a contact, one of the automatic contacts, what I'd recommend that you do is that you just suppress them. So to suppress, you just deselect it. You'll see it puts a good cross through that, helping indicate just that. Okay, so I think we're good with the setup there. Contacts have been dealt with, loads have been dealt with, materials, etc. So we'll go ahead and run this. So you see my light has actually changed to green, telling me, green light. Let's go ahead and do this. I'm going to hit the button there, and while it's solving, I'm going to check to see if there's any questions. I encourage you to fire some over while these things are going. And let's see what's going on out there. So there's a couple different questions, and I will, if you've ever been to one of my webinars before, you'll know that I might not answer them during the presentation, but I will definitely email you after if I don't actually get into it. Okay, so here's a great question. Can you input your own material properties? Yes, this might have been before I actually cover that in the materials section there, but you can definitely do that, and I'll try to circle back to do that after we take a look at some of these results. It's asking about different element types. No, currently we have tetrahedral elements only in Fusion 360, so that is the answer to that question. And it looks like I have some results there, so I'll circle back to those in due time there. But okay, so it looks like it's solved, and you'll see that only took a minute or two, so we could probably get through a couple good iterations here. It does look very blocky, and that is because I'm using these draft quality elements, the non-curve style. And when I'm looking at these results, I'm questioning these, right? We have 5 watts, which is actually pretty significant if it's concentrated. I mean, 5 watts without appropriate convection could heat up to infinity essentially. But this is something I question, because I know LED or the diodes themselves actually run pretty hot. So with what we defined in the load and convection, I'm questioning whether or not this is accurate. You see it's going from 20.97, so 21 degrees Celsius to 20. So this thing's cooling very, very efficiently. So I did something wrong there, and I did that on purpose, because what I'm trying to show you here is that, again, your first time you set up, the first time you set up a simulation, it's not going to be perfect, and it's a little bit of an iterative process, both in terms of the design approach and in the simulation setup. So I did something wrong there, and what I did is I didn't pay attention to units, and this is actually a mistake I made when I was first setting up this problem last week for the blog post that I was making there. And let's go ahead and take a look inside of my loads folder to try to figure out what I did there. So I know it's not the internal heat. 5 watts is pretty safe assumption for my LED. Let's go ahead and look at the convection. So if I edit my thermal load here, you take a look at this. I think most people define your convection values with meters squared Celsius, right? So this is in millimeters squared Celsius. So I've defined this to be a very, very, very convective surface. So forced convection with like molten metal, I think, is the only thing that could come close to what I'm actually showing here. So we don't have molten metal carrying away the heat from these surfaces. So let's go ahead and let's take a look at these different units that we can use here. So we can use this button here to override the current units and get into things like watts per meter squares Celsius. So let's go ahead and redefine this as 30 here, and we should get some better results at that point. Okay, so we'll go ahead and click OK to that, and I think that's the only thing I really needed to change here. I'm going to go ahead and just solve it again. And again, this is an iterative process in terms of the setup, in terms of the actual design changes that you're going to be doing as well. This will only take a minute or two. I think another question that I saw when I had the question panel open was whether or not Fusion 360 can do flow simulations at this point, and the answer to that is no. I can't really say whether or not that's going to happen at any point in the near future. Well, I can probably say it's probably not going to happen in the near future, but long term, there's some possibility there. But for now, it is not included in the software. Okay, so now we're looking at some more accurate results, or something that I'd expect to be closer to what you'd expect with the LED. And you can see that the diode itself is at 61 degrees Celsius. That's 40 degrees hotter than the previous case. That's what happens when you define it properly. And we can go through here and we can analyze this a little bit, maybe do a min-max plot to see the maximum point there. It looks like it's right on the top. That makes sense. It's furthest from that conducting face of the circuit board, which I made that odd material. We can do some other things here. We can create some slicing planes and cut through this model and kind of slide it back and forth and see how that heat is or the temperature is is dispersed throughout this body. I'll go ahead and OK that. Whenever I create slicing planes, by the way, I do like to go and I like to hide them. I think that it looks a lot better. Another thing I can do here to make it look a little more legible and visible is to hide the mesh. I feel like that helps you visualize what's going on there a little bit better. So that looks pretty good. But like I say, that's just the baseline setup. So now I want to go and I want to create another version of this. And this is the beautiful part about having an integrated solution, is when I want to make a design change and try something else, I can just jump back into my modeling workspace. And I'm going to show this heatsink with fin option, and I'll hide the other one. Not that it really can be shown, but here I have just a single fin on here, but let's add a couple more, right? And I don't want to get too crazy with this because it will take longer to solve with the more fins I have, because it's creating more elements, more nodes, and more mathematics that has to happen there. But I do want to do a circular pattern with this fin that I've created so far. So I do have a selection set, and all this really does is it gets the four faces of the fin. So left, right, front, and there's a bottom face there as well, and it would be more visible if I hid some of the other bodies there, but that's besides the point. So let's go ahead and just do a circular pattern with this, and I'll do a pattern with faces, and I'll select the axis, and I don't have to go and I have to select or create some axis to do this with. This conical face will work just fine. Right now there's 3 fins, and to verify that I can rotate around and look at it. But I'm going to increase this maybe to let's go to 7 or 8 or 9. And one thing I do love about these is that you can go and you can deselect 1 or 2, and this might create some interesting results, but I'm going to deselect 2 of those components there, or 2 of the pattern features. And just like that, we've created this. It's going to add a couple more fins, and I'll just use my mouse marking menu to OK that. So that's it. I mean, that's the model change I wanted to do. It's a little odd looking, I agree, but just having a little fun with that, showing you some of the options in there of what you can do with your patterns. So let's go ahead and let's create another simulation for this model. So I'm going to go ahead and I'm going to just switch back to my simulation workspace. And you can see it's telling me my results are out of date. I did make a change to the model there, and it's something that I can come back and I can fix and adjust and rerun. But really, I know what this first result does. It's 61 degrees Celsius, and so I just want to reuse these same assumptions for the second problem. So that's where cloning your study setups comes in very handy. So I'm going to right-click on my baseline analysis, the one that you saw me run through, and I'm going to clone that study. Now, when I've cloned this, it took basically all the settings from the previous study and brought them over. And there's going to be some little caveats and things that we need to work through here. First of all, I want to show and include the body that is what I'm really looking to analyze here. So I'm going to turn on the heatsink with fin option, and I'm going to deselect the hidden one, the heatsink that we used in the previous case. And that's it. I mean, that's the one change I'm going to do to the bodies folder. The materials should all be set already. If you recall, I used as original for the previous case, the no fin heatsink design. So we're good on that front. One thing that we do need to address is convection, right? The convection that I defined previously was all attached to a different body. Even though it looks the same, it's a different body in terms of my design. So this is something I do need to address. So I'm just going to right click and I'm going to edit the thermal load. And this is something that I learned a lot about, and something that I want to share with you guys, is how I was able to select these faces very, very easily. If you did read my article, I think I went up to 24 fins. So we're talking about a lot of faces, and selecting all those individually would not be fun. The other thing that's not fun is using the select all faces option. If I turn this on, and I'm just going to select maybe like the panel piece because it's only 10 faces, it does a good job of getting every single face, but I'm going to have to go through, in the case of the heatsink that I want to actually define this convection load to, and deselect a lot of the faces, like the faces on the top where the globe is actually keeping air from freely flowing around it. So I'm not going to use the select all faces option, so I'll turn that off, and I'm going to actually clear this selection currently. And to get all the faces, I'm going to use some of my selection tools. Now you have the normal box select, and that's actually what I'm going to end up using here, and that's what I use about 80% of the time I'm using Fusion 360. We have the freeform select option, which has helped me in some cases actually, and the paint selection. So be aware of those and understand that as you use these, if you go from right to left and scroll over faces, it's going to get anything that you cross over. So I'm just going to do a quick example here. Like, I'm not going to fully go through this face here, but I'm going to go right to left. You'll see it actually selects it for me. If I go from left to right with that same selection area, it's not going to get anything. So if you go left to right, it only gets what's fully encompassed. If you go right to left, it gets anything that crosses over the box. So this is going to enable me to select these fins extremely easily. So there's 28 faces that I've selected. Now, at the bottom of this, there's actually separate faces for each one of these little pieces that you see here, and I do want to get all those. So how am I going to do that in this case? I'm gonna just turn my view to just kind of be looking, directly at this from the back. It looks like if you would just use this cube up there. And I'm going to draw the cube from left to right in this case. So I'm going to just kind of cross over the area that I really want to get there, and that added a number of faces there. So I'll circle around and verify that, and it looks like it got one extra, so you can always deselect faces that you don't want to include. So I just deselected that one. Now at the top here, there's a couple more faces I want to select, so 1 and 2, and just like that, we've done 44 selections, and if I wasn't narrating it, I could have done that in probably, 30 seconds or so. So the same settings are going to be used here, and we're going to verify our unit system in use. So meter squared, I like seeing that. Okay, and the ambient temperature is going to stay the same. So I'm going to click OK, and I'm ready to run this, right? Or maybe not. The other thing is that the contacts that were there no longer apply. If I go and I try to solve this, it's going to tell me, you're missing a lot of these contacts. And this is something that I overlooked, in my first setup of this problem. So it is something that I do want to show here, but I do want to show you that Fusion, finds these missing contacts, and it shows you. So I'm going to click to create the auto contacts again, and that's going to just, replace these ones with the appropriate ones at this point. Contact creation, again, it takes a little bit of time. It's finding all these faces. It's including that tolerance that we built into it. So, and I'd be interested to see, and I haven't actually tested this, but I'd be interested to see if you turn the tolerance down to 0, if it would actually calculate this a little bit faster. But, I'll have to do that offline next time. So I'm going to collapse this down. You can see it replaced all those missing bonded contacts with the appropriate ones in this case. So we're good to go. I can go ahead and mesh and run this. I'm going to just click to solve, and we should get some results pretty shortly here. And again, I'm gonna double check to see if there's any questions out there. Okay, I got a lot of questions. I'm going to have to come back to those, and I'll email you. It's just kind of overwhelming at this point. I apologize for that. But shortly here, we should have some results. And if you recall, in the previous case, I believe it was something like 61 degrees Celsius. We'll see if this one's significantly less. And there we go. We have some results before I could even fill the dead air with my ramblings. We have some new results. You can see that the maximum temperature in this case actually dropped about 20 degrees Celsius, which I would say is very significant. So I mean, we can keep going with this. We can add 15 more fins. We can add 100 fins. Whatever we can fit in there. But we're constantly balancing the cost to the benefit, right? We don't want to make this out of an expensive material due to its highly conductive nature, or actually I've heard that some of these LED lights are starting to use active cooling mechanisms, so like fans and stuff. So those are some options that we could get into, but it's with having these tools and having this ability to test these things and do all this, you can get a lot of information in a short amount of time. So one thing that I do want to show you is how you can communicate these results to other people at your work or other people that you're working with. And so at this point, I'm going to go and I'm going to show you some of these options. So first of all, you can generate a report. And this report is going to include all kinds of information. You can actually do it for both of the studies that I have set up here. So baseline and baseline 0, which I really should have renamed to include fins or something. But I apologize about that. But we can go ahead and preview this. And you'll see that these reports will include all kinds of information. It's going to include information about the setup, about when it was run, that contact tolerance that I mentioned before, the material information, heat loads, convection loads, everything that you can imagine. That's even going to get into the results there, obviously. So that's the most important thing. So with that, I did actually want to show you some other ways that you can collaborate and share these results as well. That's not really my favorite way to share results from Fusion 360. So let's close that. It's kind of old school, right? Let's share these results with an interactive tool that's just incredibly easy to share. So I'm going to jump into my data panel at this point, and I want to just show this button here. This is actually going to enable me to look at the different iterations. First of all, if you want to roll it back to an earlier iteration. Or what I really want to do here is I want to open this in A360. By using A360, we're going to have all kinds of additional options and additional sharing mechanisms and collaboration tools. So within A360, because I use that button that was right there, it actually took me directly to it. That's unfortunate. It must still be saving. It does take a little while to get this information online. Let's use a different example here. One that I should have some results. The one I actually used for the blog article that I wrote. There we go. That's what I like to see. So in this case, I had actually run through 5 different iterations. So in A360, you can see there's all kinds of information included here. It could include your CAM data, your animations, your renderings, your simulations, etc. So here's my simulations, and I can see all the different variants, up to 24 pins, the no fin option. But I'm going to just click one of these and click the view button. And this is actually going to take me to the A360 viewer, which will enable me to do things like markup, and it'll enable me to explode and slice and do different things. You'll notice that when it was first coming in there, it actually was showing the body behind it, but once it finishes loading, we can actually rotate around and look at this and actually see the simulation results here. One thing that I do like to do when I'm using this tool is to jump in over here to the essentially like the browser, if you will. And in this case, I don't really appreciate all the different loads showing, so I'm going to hide those just real quickly, just get rid of them, just so we can look at the results here and see, in this case, the 12 fin case, the temperature got to 46 degrees. We can do a markup on here, and we can say, hey, that's too hot. Let's try to reduce that a little bit. And save that markup, and whoever I was working with would be able to see that information. And if I want to actually share this, this is great for me to see it, but it's really about other people seeing it. To share this very easily, you can click this button up here, this share button. You can actually do this directly from Fusion 360 as well, but this is another way to do it. If you click the share button here, you'll be able to provide a link to anyone that you work with to look at this on any device, on any operating system. Really, it's there's a lot of different things I can do with this. So I can just copy this. And because I'm this lonely designer all by himself, I'll just paste it into a new tab, and this is essentially what anyone will see if you send this to them. And actually, let me go into an incognito window, paste it so it's not using my login credentials to do anything special there. But this is what you're going to see here in a moment is the what you'll be able to share with anyone. And this case, it is thermal, so it is. Jump into the simulation itself here, and you can see that it was just showing the model at the very beginning there. It's just the way that it wants to do it by default using that share link. And you see that I have also, in addition to the model, I have animations. I have every single analysis that I had run on this. And again, I can go and hide and show things. I can explode it. I can do slicing planes. I should note, however, that the slicing planes within this tool is not going to enable you to visualize the simulation results through the model, but it's going to just slice it. Hopefully that functionality is going to be there shortly, but there we go. We can see in this case, this is the 24 fin case. It was just slightly lower in temperature, so just some information to consider and another way of sharing your results. So I did just want to kind of recap by going back into my PowerPoint just to talk about, setup details. Just work your way from the top down. These are showing my static stress, my stress strain analysis loads. Obviously, you're just looking at a thermal case, so it's a little bit different. Your results, make sure that you understand how to do a lot of post-processing. And again, that's something that I covered in another presentation at an earlier time. One thing I was messing around with in this case was I put this information into Excel that I was able to gather from this. So I was looking at fin count to the diode temperature, and I tried to do a little bit of curve fitting. The first time I did it, I did a polynomial curve fit, which worked up to about 40 fins, and then it started going back up, and that's not really what you'd expect to see. So I kind of do this in every simulation presentation I do. I do want to make sure that you know where to go to find different materials. If you don't find your material in our database, you can go to things like MatWeb. There's military spec sheets that include a lot of information like that, and even vendors can include information like that. We do have additional learning resources. Again, check our YouTube channel. We update that all the time, and there's a lot of different people contributing to it. There's a lot of simulation things in there. There are some built-in tutorials, but right now it's somewhat limited for simulation. So hit me up. Let me know if you have questions. I'm always happy to help, provided I have time. I do like to show this, and I think I demonstrated actually in the opening for this presentation, talking about running through the calculation, making sure it's right before duplicating it and running it 5 times over. You want to make sure it's right the first time, you want to make sure that you iterate on the actual setup to ensure that the setup's correct. But check your setup. If you're getting results that you don't trust or that seem wrong, check your materials, check your loads, contacts, constraints, and remember, in the end, this is a numerical technique, so being within 5 to 10% of some empirical data is actually pretty amazing. So I will say that. With that, I think I'm going to conclude this. If you do have questions, you can tweet at me. You can send me emails. I'm going to respond to everyone who wrote me a question. Usually it takes me a good couple hours, though, so don't expect that immediately. But I appreciate everybody's time. I hope everyone learned something new. I used a slightly different approach in this webinar. In this case, I did want to actually spend a lot of time in Fusion and working on the same problem. I think it's kind of a coherent message. I hope everyone appreciated that. With that, I guess that's it. Thanks for your time. Keep sharing your amazing designs with us. We love seeing them. So have a great day, everybody.